for system resultants, statics of rigid bodies. So at the end of this session, you guys are expected to, one, be able to discuss the concept of a moment of a force and show how to calculate it in 2 and 3 dimensions. Next, be able to provide a method for finding the moment of a force about a specified axis, define what moment of a couple is, present methods for determining the resultants of non-concurrent force systems, and indicate how to reduce a simple distributed loading to a resultant force having a specified location. So we start by studying moment of a force. Now, it is said that as you apply a force to a body, it will produce a tendency to rotate and about a point that is not on the line of action of the force. Now, this tendency to rotate is sometimes called torque. Now, more about torque will be discussed in your strength of materials. I believe in your prospectus, they call it the fundamental of the mechanics of deformable bodies, but nevertheless, uh, it is still the strength of your material, meaning you'll be considering deformation that the applied force causes or the resulting deformation due to the applied external force. Now, but most often it is called the moment of a force or simply the moment. Now, the magnitude of the moment is directly proportional to the magnitude of your force multiplied by the perpendicular distance, or we call that our moment arm. Of course, the larger the force or the larger the moment arm, the greater the moment or the turning effect. So if we can observe that in our wrench here at the figure, if the perpendicular distance is shorter, we need to exert more force. However, if our distance, perpendicular distance is larger, or yeah, our force will be exerting lesser force. Now, note that if the force F is applied at an angle theta, which is not equal to 90 degrees, but of course greater than 0, it will still produce a moment. However, it will be very difficult to turn the bolt since the moment arm, which is represented by our d prime here, which is equal to d sine theta, will be smaller than the distance where we apply our force or where our hand is. Now, if F is applied along the wrench, its moment will be 0 since the line of action of F will intersect point O. As a result, the moment of F about point O is also 0 and there is no turning can occur. So, sabi ni siya, if imong birahon ang imong wrench, di ka makapatuyok sa imong bolt. So, of course, magnitude of moment is force times distance. Now, this is not the same with work in your physics because work is created when you apply a force to your object and that object produces that due to the applied force, your object moved at a specified distance, at a particular distance. But no, here, it's more our moment arm or perpendicular distance is like the force applied at a specified point, kung asa ang point. Now, units of moment magnitude consist of force times distance or in Newton meter. Now, for SI unit, we will report our answers in Newton meter. So if our distance is in mm or in cm, we must convert that back to meters. However, in our English system, if your given distance is in inches, you don't have to convert that to feet. So you report your answer in pound inch. And in if your given distance is in feet, then you don't have to convert it back to inches. You just report your answer in pound foot. Okay. Now, the direction of moment is determined by its moment axis, which is perpendicular to the plane that contains the force F and its moment arm D. The right-hand rule, which was already shown to you guys, I'm just re-recording this one for you for your consumption if you want to do some review. According to this rule, the natural curl of our fingers of our right hand as they are drawn towards our palm represents the rotation. Or if no movement is possible, there is a tendency. So of course, since we are studying statics of rigid body, static meaning in equilibrium, uh, no movement, and we assume that our body is rigid. So of course, there is no rotation. More about rotation will be discussed in your dynamics of rigid bodies. So in here, although we would say moment, rotation, we are referring to actually to the tendency for rotation. So we're about to rotate caused by the moment. Now, so for two-dimensional problems where all the forces lie within the xy plane, the resultant moment, which is m sub r, quantity sub o, about point O, can be determined by finding the algebraic sum of the moments caused by all the forces in the system. So, of course, as convention, we will generally consider positive moments to be counterclockwise since they are directed along the positive z-axis, meaning it follows the right-hand rule. If we put our right hand on top of our left palm, and we try to curl our fingers, it follows a counterclockwise movement. So that is a positive moment. And clockwise moments will be negative. Now, by doing this, the directional sense of each moment can be represented by a plus or minus sign. Using this sign convention with a symbolic curl, so when we say symbolic again, we're just referring to, so if we do moment, we assume and write small curl, then positive. So assuming counterclockwise positive. To define the positive direction and the resultant moment is therefore the resultant moment m sub r is equal to the sum of all the moments, and our moment has a formula force times distance. So feel free to see the video for example 2, 3, 4, 5, and we already did 5 to 6. So the video will start at example number 7, I believe. Okay, now the principle of moment, if you can observe that if we go by the definition of moment, which is really find for the perpendicular distance of our force, it tends to be troublesome, right? Now, that is why a new concept, which is the principle of moment, is introduced. Now, a concept used often in mechanics is the principle of moment, which is sometimes referred to as the Varignon's theorem. Now, others call it Varignon. It's completely up to you. Now, since it was originally developed by the French mathematician Pierre Varignon, it states that the moment of a force about a point is equal to the sum of the moments of the components of that same force about a point, especially to those forces that are applied at a specific angle with respect to the horizontal or the vertical. So let us say for our example here, this angle is applied at a certain angle from our horizontal, which is theta. Therefore, by following Varignon's theorem, we can solve for the moment that this single force caused about point O by resolving that force into its x and y components. So that is f sub x and f sub y. So of course, if our theta is measured from the horizontal axis, meaning x-axis, so our f sub x would be cosine theta, and f sub y would be sine theta. But be very careful again, that doesn't mean that all y should be sine and all x will be cosine, because if that theta there is applied, is measured from the positive y axis, so let us say this one here, let us have that as beta. So for our y, it will become cosine beta, and for our x, that becomes sine beta. Okay, now for two-dimension problems, as in the figure on the right, we can use the principle of moments by resolving the force into its rectangular components and then determine the moment using scalar analysis. Thus, this is assuming clockwise positive, right? So f sub x times y minus f sub y times x. And although in our illustration here, it assumes clockwise to be positive, but for our succeeding examples, we always assume counterclockwise is positive for uniformity. But this is just to show that whatever assumption you do, you just have to follow what is uh, you just have to follow accordingly. So it's completely up to you. If you want clockwise to be positive, then no problem, because eventually you will end up with the same answer. Now, but before we proceed, and not really before we proceed, but before you go to the examples, which will be provided, well, in comment section, Uh, we will tackle first the principle of transmissibility. Now, this principle states that the conditions of equilibrium or motion of a rigid body remain unchanged if a force F acting at a given, for a while, okay, at a given point of the rigid body is replaced by a force we call F prime of the same magnitude and the same direction, but acting at a different point provided that the two forces have the same line of action. So let us say I have here my rigid body, which is a truck, and I apply force F of a certain magnitude at the front. So of course, that force is applied at a certain height from my datum. This is my datum, meaning the floor or the road or whatever. It is the same as if I am pushing my truck with the same magnitude at the back. And it follows the same line of action. So it means the height must also be the same, which is y. Let's call this y1 and y2. So y is equal to y1 is equal to y2. And that is the principle of transmissibility, which is very essential in our upcoming examples. So please see in the comments, wow, the video for example 7, 8, 9, 10, 11, and yeah, 8, 9, 10, 11. So next would be the moment of a couple. Now, a couple is defined as two parallel lines that have the same magnitude but opposite directions and are separated by a perpendicular distance d. Since the resultant force is zero, the only effect of a couple is to produce an actual rotation, or if no movement is possible, there is a tendency of rotation in a specified direction, right? So it must be the requirement is that they have the same magnitude, they act at opposite directions, and they must have a perpendicular distance that separates the two. So those three are the requirements for a force to be considered as a couple. Now, the moment produced by a couple is called a couple moment, and we can determine its value by finding the sum of the moments of both couple forces about any arbitrary point. Okay, so again, examples will be provided. So the moment of a couple M is defined as having a magnitude of M is equal to FD. Yeah, we will just have to use one force times its perpendicular distance. So it means that, let us say, if you have your systems here, you have another force there, going down force. It means, let us have this as F sub 1, F sub 2, and we take the moment about here. Okay, so we have moment is equal to F sub 1 times its perpendicular distance from, let us say, this is O, from O plus, or I'm not following the correct sense here, F sub 2 times its perpendicular distance from O, and then we add this couple here. So let us say, usually uh for our couple, usually it is given a certain value, let us say at 400 Newton meter. So you just add 400 Newton meter here. Now, of course, we add or subtract our couple depending on our assumption. So let us say if we assume counterclockwise positive, and this couple here going to the right, going to the left, going to the right, creates a counterclockwise moment, so therefore we add. Okay, but if we have our couple is going to the left and going to the right, ang bottom, going to the right is the upward part, and the going to the left is our bottom force, and it creates a clockwise moment, so we subtract 400 Newton meter. And don't worry, it is provided in the example, where F is the magnitude of one of the forces and D is the perpendicular distance or the moment arm that separates the two. Now, the direction and sense of the couple moment are determined by the right-hand rule, where the thumb indicates this direction when the fingers are curled with the sense of rotation caused by the couple forces. So in all cases, M will act perpendicular to the plane containing these forces. Okay, so the representation would be, so if you have your big wheel here, so if they are, and its diameter is 0.4 meters. So if you pull the uh, your right arm, your right hand towards you, you push your left hand palayo sa imuha at the same magnitude, which is 30 Newton. And of course, if you have it, you apply your forces at a much closer distance to your where rotation might occur, the center point, you will be exerting a much greater force compared to if layo siya. If two couples produce a moment with the same magnitude and direction, then these two couples are equivalent. Notice that larger forces are required in the second case to create the same turning effect because the hands are placed closer together. So when I say they are equivalent, because if you multiply 30 with 0.4, 30 times 0.4, that creates a 12 Newton meter moment. And if you multiply 40 with 0.3, it still causes a 12 Newton meter moment. Okay, so a video for 12 is provided, 13 as well, and next would be, sometimes it is convenient to reduce a system of forces and couple moments acting on the body to a simpler form, right? By replacing it with an equivalent system consisting of a single resultant force acting at a specific point and a resultant couple moment. So a system is equivalent if the external effects it produces on the body are the same as those caused by the original force and couple moment system. In this context, the external effects of a system refer to the translating and rotating motion of the body if the body is free to move, or it refers to the reactive forces at the supports if the body is held fixed. Now, of course, for this in statics or of rigid bodies, we are much concerned with the reactive forces. Less we will more on translation and rotation in dynamics of rigid body. So what does it mean is that if you have your system of forces just such as this one, we have moment, no, weight one of our first traffic light and weight two of our second traffic light. So what we can do is we can also we are allowed, it is okay to express these two forces weight as a single resultant force, and that is it acts here. So that is weight R is equal to W1 plus W2. And of course, we take moment, it creates of this these two forces creates a counterclockwise moment about point O. So we are allowed to do that, especially if the system gets to be very complicated, especially if we have so many forces that acts on our specific of our on our rigid body. So we can just have the resultant force and calculate the moment using that resultant force. So we have examples for that as well. Just see the comment section. Wow, diba? Now we have example 14, example 15, example 16, and 17. Then we have 18, 19, 20, and 21. Next is sometimes a body may be subjected to a loading that is distributed over its surface. So sometimes instead of just a single force, we have a system of force. Let's say if this is a cantilever beam, that this and it is applied here, of course, this beam has its own weight, right? And it is distributed. So we have distributed over a specific length. This is what we call uniformly distributed. Good if our force is uniformly distributed, but there are cases wherein our force is varying. So we have your triangular loading, for example, yeah. And we have varying. So say cubic, for example. Ayun. Oops, let me delete this part first. Now, sometimes a body may be subjected to a loading that is distributed over its surface. For example, the pressure of the wind on the face of a sign, so like you are facing the sea and then a certain wind hits you, the pressure you can feel more like the amount of force is applied over your entire face. Okay, then we have the pressure of water within a tank. You will encounter that if you have fluid mechanics in your third year, or the weight of sand on the floor of a storage container are all distributed loadings. Now, the pressure exerted at each point on the surface indicates the intensity of the loading, and it is measured, of course, in our physics. You encounter the Pascal, the unit Pascal, which is Newton per meter squared in SI unit. Now, the most common type of distributed loading encountered in engineering practice can be represented along a single axis. Now, if you can recall in your engineering drawing, so if you try to see the isometric view, so you have your rectangular, right? This is then, right? So if your body is uniform, you can just view it as 2D. We just have to multiply. So of course, this is in Newton per meter squared, right? So you just have to multiply this one with this length, or does it your width? Yeah, your width. Let's multiply that with your width, which is in meter. So you will only end up with Newton per meter. So you can now view your loading as two dimensions. So for two-dimension loadings, it has a unit of Newton per meter, meaning your force over a certain length. Okay. Mhm. Okay, now, for example, consider the beam or plate that has a constant width and is subjected to a pressure loading that varies only along the x-axis. So, yeah, it varies only in the x, not in your z. This loading can be described by the function P is equal to P of x, pressure as a function of your length, which is Newton per meter squared. It contains only one variable x, so we can only also represent it as a coplanar distributed load. And to do so, we will multiply the loading function by the width b, m, of which has a unit of meter or m, so that w, our weight of x is equal to P of x times your b, right? So this is our b. So this becomes now weight x. Okay, so formula, the magnitude of the resultant force is equal to the area A under the loading diagram. So for this is our loading diagram. And we'll use integral, so meaning our resultant force is equal to the integral over the entire length of W of x dx. And we know Wx dx is equal to the differential of our area dA. So for our resultant force, that is equal to A, or the area. Good if our uh, loading is follows a regular polygon. So let's say square of a rectangle or a triangle, because their areas is defined already. So for area for a rectangle is 1/2 base times height, and for our rectangle, that's base times height, right? But for variable varying loading, such as this one, our letter B, we will be using integration. And to locate the force, the resultant force has a line of action which passes through the centroid C, or we call that the geometric center of the area under the loading diagram. And to calculate that, bar x is equal to the integral of x times W of x dx, integrate it over the entire length divided by W of x dx, and we integrate that as well over the entire length. And we know that Wx dx is equivalent to our differential of our area. So x times dA, we integrate it over the entire area divided by the integral of dA. We can calculate our bar x, which is the uh, what do you call that? The centroid. So for our triangle, that don't worry, I will be uploading in the our Google Classroom the formulas for the centroid or geometric centers for regular polygons. But for varying loading, we'll be using integration man. Okay, so like I said, for our triangle, from the tip, so if this is our triangle, from here, this is 2/3, and from here, this is 1/3. So examples will also be provided for example 22, 23, 24, 25, 26, 27, and just see the links at the comment section. So if you have questions, feel free to send a chat or an email.